Okay, we're going to start. Welcome to the fourth lecture of quantum optics with atoms. And it's in charge, Morgan is in charge, and he will talk about limits on detection. Thanks.
Okay. Thank you for the introduction. Can you hear me okay? Is the microphone working? More, less? It's okay? More? They say more. Dicen más. Okay. Okay, so tal vez un poco menos. Okay. Okay, good. So what I talked about last time was how we could generate non-classical states like squeezed states using, in the optical case, a combination of a pump laser and a nonlinear material in order to generate a Hamiltonian that had a particular form. And that form gave us a squeezing, and we could see the squeezing through quantum dynamics. So we had quadratures, and when we applied this Hamiltonian for some time, it would stretch our state in such a way that it produced squeezing. And we understood that that corresponded to the squeezing that we needed for the interferometry applications. Okay, so in some sense that was warm up. I would now like to talk about how you do that with atoms. And I need to tell you what the phase space is, and I need to tell you what the squeezing operators are and things like that. So again, phase-space methods, uncertainty relations, operator evolution, and dynamical squeezing. Okay, and I'm going to introduce this topic through atom interferometry because it's a very interesting topic. It's a very interesting topic, and it also is good for illustrating the things that I need to illustrate, which are especially the Bloch sphere description, the single atom Bloch sphere, and then many atom Bloch spheres. And then I can show how that gives sensitivity in an instrument, and then I can show how to generate spin squeezing and why, and then what that means. Okay, and then if I get to the end, I will talk about quantum limits of magnetic sensing and somehow why a Bose condensate is at present the best magnetic sensor. Okay, so atom interferometry. This is an atom interferometer. This is the kind of thing that Giovanna Palacios' company builds. This is not built by her company. This is built by a European company, and it is sitting next to a European volcano, which is Mount Etna. And what this is measuring is the gravity in this location. It's a portable device. You see that it's sitting here outside. And it's able to see the movement of magma under the ground by the gravity that it creates. And so that's a very impressive feat to be able to do that. Say something about where gravity measurements come from. So the first gravity measurements were pendulums. So you have a pendulum and you know that its frequency depends on the strength of gravity and the length, and you can measure the length. And then if you have a good clock, you can measure the frequency, and then you know the gravity in the location where you are. Those are not particularly accurate, but in the 19th century, that was the best you could do. And you can see that people put effort into them. Okay, then when we get to the 20th century, then we get some electronic technologies, and we get better gravimeters. So this is based on a spring and a mass and another spring here. And then to see how far gravity has pulled this down, then you can use a light bulb and a photocell and get an electrical signal, which tells you how strong gravity is. You can also do this electrically using capacitance. Okay. But when we get really good gravimeters, so microgravity precision instruments, it's because we start to use quantum effects and we start to use interferometry. Okay, so this is a corner cube, a falling corner cube interferometer. There is a laser which hits a beam splitter. The big beam splitter is fixed in place. One beam goes to the photodiode, another beam goes up, reflects off of this corner cube, reflects off of another corner cube, and gives you fringes here. And then the photodiode tells you what the difference in phase is between this path and this path. And then you drop the corner cube, and you see those fringes change in time, and that looks like this. And you see, as the corner cube is accelerating downward, the rate at which the fringes happen is growing quadratically, and you get a phase which is G, the local gravitational field, K, the wave number for the light, and T squared, the amount of time that has passed by. So again, if you have a good clock, then you can record these things, and you can get a very good measurement of the gravitational field. And this is somehow the standard technology that is used in things like mining and geophysics. Okay, and then this is a paper from 2018 where they demonstrated 10 to the minus 9 G. So that's ridiculously good accuracy on the measurement. That's again with one of these systems. This is from a different European company. And the way this works is based on cold atoms. So you start by collecting cold atoms up here, you allow them to fall, and as they fall, you're manipulating them with lasers, and the lasers cause state changes that are associated also with changes, internal state changes that are associated also with center of mass motion changes. Right? And that center of mass motion allows you to get the gravity. Okay, so to make sense of this, we need to think about internal states and external states. So I'll look at our favorite atom for most sensing, which is rubidium-87. So that has a nucleus with spin 3/2, has one valence electron, which then means that the electron spin is 1/2. And those can combine to give you different total spins. The ground state is this 5s1/2 state. That's the inner shell electrons are in a krypton configuration, and then there's the one valence electron. So looking at just at the spin parts of this, the nuclear spin can take on 4 values. The electron spin can take on 2 values. And in the basis of nuclear and electron spins, then you can have any of these times any of these. So you have 8 total. Then the electron spin and nuclear spin are coupled by the hyperfine interaction. So if you look at the energy eigenstates, they're not eigenstates of these operators, but they're eigenstates of the total spin. And then that can take on 2 different values. It can either be F equals 1 or F equals 2, and F equals 1 has 3 possibilities, F equals 2 has 5 possibilities. So that again is 8 states, just as you had here. And these are all superpositions of combinations of these. Then our favorite excited state is the 5p3 state that now has a different value for the total electron spin, so including the orbital angular momentum. And that gives us 4 times 4 states, which is 16. Which can give us, by adding these in different ways, we can get from F equals 0 up to F equals 3, and there are a total of 16 states here in the excited state. So these are internal states of the atom. There are a lot of them. We would like to be able to work with something simpler, and almost always when we work in sensing, we pick some subset of these. So for example, we could work with just these 2 states. So this is a clock transition. Neither of these states is affected by the magnetic field. And so the frequency here makes a very good reference for atomic clocks. In atom interferometry, then it's common to work with these 2 states, which are connected by an excited state through a Raman transition. And so we can focus on these 2 states for the next part of the talk. Okay, so now imagine that we have an atom that's in one of these states, and we hit it with lasers, one of which is sigma plus polarized, so it can drive this upward transition, and one of which is sigma minus polarized. It could drive this transition, But since the atom started here, the atom will make an upward transition, and then it will make a downward transition here, stimulated by this laser. Okay, so when that happens, the atom is going to get a recoil of 2 h bar k, one from absorbing and one from emitting in the opposite direction. Okay. Then we can continue to illuminate with the same lasers, and they can drive a process where the atom goes from the state back to the original state, and in doing so, it loses that 2 h bar k. Okay? And we can also do coherent things in between, that if we leave these on not for long enough to make the full transition, then we can go from this state to a superposition of this and this, and that now gives us a two-state space that we can coherently manipulate. Okay? And so that's exactly what's happening here, that the atoms, they drop, they experience first a pi/2 pulse, which generates the superposition, then a pi pulse, which reverses the superposition, and they fall a while longer, and another pi/2 pulse, which can take them either to f = 1 or f = 2, depending on how much phase they acquired in the intermediate time. Okay, here's a representation of that. Time on this axis, height on this axis. The first pulse splits them, the second pulse reverses them, the third pulse recombines them. And it turns out that the phase that you acquire in this is exactly the same as it was in the dropping corner cube experiment. Okay. So why is this better? Why does this do better than the dropping corner cube? Does anyone have a guess? No guesses? Is it because atoms are massive and photons are not? And so the de Broglie wavelength of the atom is much, much shorter than that of the photon? I see some people nodding. Does anybody think that's not the answer? That's not the answer. The phase is the same. Okay, the phase it does not have the mass of the atom in it anywhere. It does have the wavelength of the photon in it, and so it's in fact the light that is giving us the phase in both cases. But still, this is a better technique. Why is it a better technique? It's because it's fully quantum. It's because the thing which is giving you the signal here is an atom. Every atom is exactly the same. And because the light that you're using is coming from a laser, which you can tune exactly to the resonance that you want. And so that can be the same. And so you can run this today, you can run this a month from now, and it will give you exactly the same response to gravity. Okay? So somehow the fact that this is an absolute gravimeter is its strength. Okay. So now we'd like to just be a bit more formal about this. I have two states in my atom interferometer. I'm going to call this one minus and this one plus. And then since I'm doing quantum mechanics with it, I need a Hilbert space. The Hilbert space is just the state space that spans these two states. And then I need a set of operators to describe operations on that space. And since it's a two-state space, then I can do a full set of operators using the Pauli matrices. And we write these, call these pseudo spins, and we write F to describe the three components. Okay? So there are three operators here for the three Pauli matrices. And then these, because of their definition, they have a commutation relation that the commutation of any two of them is plus or minus I times the other one. Okay. Okay, and so then the block sphere representation is to represent on a sphere the average values of these, and in that way we can specify a state. The state that's here has Fz positive, and so it's up here. The state down here is Fz negative, so it's down here. These superpositions would have Fx either positive or negative, and that gives us a visual representation, and it also connects us to rotations because this operator, e to the I angle times Fz is a rotation by that angle about the z-axis. And so a lot of the things we can do, we can understand in terms of rotations on a sphere. So in particular, here, we start with the atoms in one particular state, in the plus state. We do the pi/2 pulse that takes them, rotates them about the x-axis down to the equator. Then gravity is allowed to act for a time. And so that gives us half of the phase that appears in this problem. So that rotates it about this axis, gives us a point here on the Bloch sphere. Then we do a pi pulse that flips it over to the other side. It experiences the second half of the phase in this time when it's recombining. And then the pi/2 pulse finally tips it in the z-axis, tips it so that its angle here now becomes an angle on this other circle. And that then is something we can detect by detecting whether it's in the excited state or the ground state, so that, for example, the probability to be in the excited state is now related by this sign to the to the angle that it acquired. Okay. Any questions about that? Who has seen this before? Okay. Okay, so we want to be able to describe an entire interferometer. We don't do interferometry with one atom at a time. And so we would like to generalize this to something that can work with many atoms. So we now have many atoms. We need a Hilbert space for them. That is just n, it's just the direct product of n copies of the single atom Hilbert space. We need operators. Those operators will be collective operators, which is to say it's the sum of the individual operators. Okay. And it turns out, because this is an angular momentum, and this is then a sum of angular momenta, then this is a sum of angular momentum, which is an angular momentum itself. And so these also obey the commutation relations. And then that allows us to, one, get something which we didn't have in the single atom picture, which is an uncertainty relation. So this commutation relation implies this uncertainty relation. If I take any two pairs of these, then they're in an uncertainty relation with the third because of this Robertson-Schrodinger uncertainty relation. Okay. Then to describe many atoms that are all initialized in the same state, we take a direct product of single atom states, each of which are along some particular direction. Y is convenient for this example. And then I can look at, given this definition, I can see the average value for F is going to be n/2, because for each one, Fy is 1/2, and there are n of them, so it's n/2. And then the uncertainty relation tells us that the uncertainty in each of those, if they're equally uncertain, is square root of n/2. Okay, and so we represent this, again, using the Bloch sphere. Now we make our point here fuzzy to indicate that there is some uncertainty about exactly what the components are. Okay, the uncertainty, if I look at the angular uncertainty, then that's looking at the uncertainty along some direction, say x, divided by the distance from the equator. And using these, then I get this angular uncertainty is 1/square root of n. Which should not be surprising. I have n two-level systems, and their phase uncertainty is 1/square root of n. And for the state that has exactly n particles in it and spins, then the uncertainty in the y direction, along the direction that's polarized, is actually 0. Okay, then rotations. If this was a rotation about Fz for a single atom, then this is a rotation about Fz for n atoms. Because this is a sum of individual spin operators, and because it's inside the exponential, then this can be expanded into this product. And we understand that just as the single spin rotator for the first spin times the rotator for the second spin, and so on. And so that means that when we apply this this operator, then it rotates us on the block sphere. It rotates the whole thing, including the uncertainties and the average. Okay, it's also possible to deal with density matrices, with states that have an uncertain number of atoms in particular. And so here it can go from a wave function to a density matrix, and with different probabilities to have different numbers. And that has a simple effect. The uncertainty on, the average value for Fy is now just the average value of n over 2. The uncertainties involve, again, the average value. And the angular uncertainty also involves the 1 over square root, is 1 over square root of the average value then. The thing that we gain by using a density matrix is that now, because the number of spins is uncertain, that means the projection onto this polarization direction, into the y direction, is also uncertain. And so now we have also an uncertainty for the for that component. Okay, so now we can look at an interferometry protocol that we first tip to get to the equator. Gravity is allowed to act. We tip again, and then we can detect the component along the z direction, which is to say we count how many atoms are in f equals 2 and how many are in f equals 1. And we can say something now about the sensitivity to this angle, and thus to gravity, which is what we're trying to measure. We can calculate the uncertainty on Fz by rotating this uncertainty ellipse so that it's in that position. We can calculate the average, also doing this rotation, and we get these trigonometric functions. So this that we've seen before, this is new. This is something that we get from the many atom representation, and now we can apply those. This looks okay. Okay, so as a function of theta, then Fz is on average this blue line, and then it can be larger or smaller, and the uncertainty is given. So this red band shows the blue line plus or minus delta Fz. And so it can be larger or smaller, but because this gets small at certain points here, 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 then we don't see the same uncertainty in each location. Okay. So now imagine that you did an interferometry protocol, you saw some value for Fz at the end. So you saw some value of Fz, and then you want to interpret it. Well, you think this Fz corresponds to this value of phi, but it could be as small as this, or it could be as small as that because of the uncertainty here. If you saw a larger value of Fz, then you would do the same calculation. You would get a different most likely value for phi, but you would still have the uncertainty here. And if you use the propagation of error formula to figure out how uncertain phi is, it looks like this, and you get 1 over square root of n. So this is then what's called the standard quantum limit. If you want to measure an angle using n spin 1/2 particles, then this is the best you can do with this fully polarized state. Okay. I just want to say it's important to be careful with the assumption that you'll have n particles. If instead, you see that? If instead I have an uncertain number of particles, then I have an uncertainty in the y direction, which contributes to this total uncertainty. And so I end up getting not that uncertainty with the cosine in it, but an uncertainty that does not depend on the angle. And as a result, I have as much uncertainty here as I do here. And when I do the same calculation, if I get this value, which is close to 0, thus close to this 0 crossing in phi, then I get a smaller uncertainty than if I get a larger value. And in that case, assuming an uncertain number of particles, then I get a different standard quantum moment. Okay. Okay, and then we have an uncertainty relation for the spins. We know the uncertainty for a fully polarized state, and we can also think about using the uncertainty relation, making the uncertainty in one component, for example, this component smaller at the cost of making the uncertainty in the other larger. And since this component is the one that gets measured eventually, then we can get an uncertainty that is less than 1 over square root of n, which is to say we do something which is sensing, which is beyond the standard quantum limit. Okay, and then you can see how far that could possibly go, that if I take this uncertainty relation, and sorry, if I take the phase uncertainty relation, and I substitute this delta fx, delta fz for the average of fy, then I get that delta phi has to be at least as large as this. And thinking about delta fz cannot be larger than the maximum fz minus the minimum fz. And so that is then n over 2. And that gives us delta phi is greater than or equal to 1 over n, and that's known as the Heisenberg limit. So with spin squeezing, you could, in principle, get to this 1 over n uncertainty, which is much better than this 1 over square root of n uncertainty if n is large. You have a large number of atoms. Okay, so how would we generate spin squeezing? This turns out to be a good Hamiltonian for generating spin squeezing. It's called the one-axis twisting Hamiltonian. I think that will become clear. If I look at how y changes, I'm sorry, the coordinate system has changed here. So now x is in this direction and y is in this direction. So if I want to know how y changes, then again, I use the Heisenberg equation of motion, and I have to calculate this commutator of Fy with the Hamiltonian, which then has 2 Fz's. And so commutator of Fy with product of 2 Fz's looks like this. We can simplify that down to I Fx times Fz plus Fz times Fx. And since Fx is large, then I can take that to be its average value, and I get this. I get this simpler form that involves just an Fz component, but it means that the time rate of change of Fz is now approximately Fy is approximately Fz times Fx. Fx is some large thing that is approximately constant, but Fz is still an operator. And so that means that different parts of this probability distribution are going to move in different ways. In particular, the part of this distribution which has positive Fz is going to move in the positive direction. The part that has negative Fz is going to move in the negative Fy direction. And points in between will move less, will move slower. And so that allows us to create a shearing of the probability distribution so that it goes from this toward increasingly sheared distributions. And so that then creates a squeezing. The component that is squeezed is this one where it's narrow. The one that's anti-squeezed is this one where it's extra wide. Okay, so how would you possibly do this? So this is how would you generate this kind of Hamiltonian? And this is something that has been done a lot in the ultra cold atom community. It's good to have a BEC to do this. This is an example. This is a paper from 2010 from the University of Heidelberg. And what they did was to use these two states, again, as their states. Their system is a Bose condensate in an optical dipole trap with a 1D lattice. And the effect of that is that they have a bunch of BECs that are all side by side. They have their lattice sufficiently deep that there's no tunneling between them. So you can think of this as independent BECs that are all doing the same thing. And then when they read out, they use Stern-Gerlach imaging, which allows them to separate this state from this state magnetically, and then they image. So this is one of their images that they get at the end, and it shows this many atoms in this BEC were in F equals 2 state, and this many atoms were in the F equals 1 state. So they have a system that allows them to do the measurements that needed at the end in order to get this to get measured this FZ component. Okay, and so thinking about just one of those BECs, and it has a number of atoms in F equals 1, a number in F equals 2. The Hamiltonian that they use comes from collisional interactions. So looking at this first term, there's a contribution to the energy, which is proportional to the number of atoms in this state times the number -1. That's the number of pairs that can collide with each other in that state. And then this is the scattering length for F equals 1 atoms with F equals 1 atoms. And then here you get the same term for the F equals 2s. So you get, again, n times n minus 1 times the scattering length. And then collisions between these will give you an energy, which is number in this state times number in that state times the interhyperfine scattering length. And so that doesn't yet look like the one-axis twisting Hamiltonian, but if we remember that our Z component is the difference in number, Z squared is then this, which is now a second order polynomial in NA and B, I'm sorry, that should be N1 and N2. Oh, right. Okay. Yeah, so it's this second order polynomial in N1 and N2. And then using those definitions, we can reorganize this, that this is also a polynomial that's second order in N1 and N2, and we get that the Hamiltonian looks like this. So it has a JZ squared in it, which is exactly what we wanted to get, and it has a prefactor which gets the contribution from these collisions and from these collisions and from these collisions. And then there's another term, which is JZ. So that means that in addition to the squeezing, there is going to be simultaneous rotation around the Z-axis. Okay, and then it turns out that rubidium-87 is particularly nice for this because the scattering lengths are almost the same, but in particular, this is almost zero. That you get a cancellation due to the interhyperplane scattering being the arithmetic mean of the two individuals. And that means that this is off, this term is absent unless you do something. And so that's the situation that they would like. They use a Feshbach resonance to adjust this one so that they can turn it on when they want to, and otherwise it's off. Okay, and so this is again the same paper, this is data, and this shows the shearing. This is illustrating the shearing process. They first shear, then they rotate by some angle, and then they measure the number. They measure the number in F equals 1, F equals 2, and they measure that JZ component. And then they do this many times and they get statistics. And what they're plotting here is the variance of this measurement as a function of the rotation angle. And what they see is that if they rotate so that the thin axis here is along the Z direction, then they see a much lower variance than they do if they rotate so that the long axis is along this Z axis. Okay. And so that's something which has been used a lot and can generate a lot of spin squeezing. Okay. How much time do I have? 20. Okay. Plenty more than I. Okay. Good. Okay. So that was for atom interferometry, and also something in general about how we describe spins, large collections of spins, and and something about spin squeezing. My topic is magnetometry, and I'd like to get to the magnetometry so I can talk about how well it's possible to measure magnetic fields. Okay, so I showed you a number of different applications. So from the very small to the very large, we'll say now a little bit about these two that are in the middle. Okay, and there are lots of sensors which are used for different, to approach these different size scales. So in particular, I will talk first about atomic vapors, and then I will talk about squids. Okay, so this is, it's wonderful for me to be able to talk about this topic in Mexico City. I've been talking about this particular material for decades now. So this person, Sheldon Briner, was a neighbor of my parents. He lived in the same town as my parents. And he is a key figure in the application of magnetometers to many things. So he was there when they were when atomic vapor magnetometers were first invented, and he applied them to looking for underground structures, minerals, skiers that had been lost under the snow. There is a famous case where an American plane with a nuclear weapon on board crashed and fell into the sea off the coast of Spain, and that was found using magnetometers to find the steel parts of the plane. And if you want to, he has passed away, but if you want to read about his exploits, then you can still see them on his website. He also started a company, so I think this is it's one of the first quantum technologies companies using atomic interferometers in order to do things like looking for mineral and oil deposits. And like a good American in the 1960s, he would wear a tie when he was out in the field collecting data. Okay, so that's what he did for a living. And what he did for fun was this. So this is him in Mexico, southern Mexico, on a horse with a magnetometer. So the atoms are up here, the electronics are back here to keep them far away. And he went into the fields with his magnetometer. Can you see this? And he made maps of the magnetic field. And this is the Earth's magnetic field perturbed by any magnetic things which are under the ground. Okay, and so that's why it's interesting for looking for minerals and things like that. And he would see things like this, and I'm sure you can't see here, but the Earth's magnetic field is about 60 microtesla, and the numbers here are about 100 nanotesla. Okay, and so he's measuring with precision the strength of the magnetic field, and he sees something here, which is the signature of some buried object that has a magnetic susceptibility. And then he excavates and he finds this, which you can see in the Museum of Anthropology. So that's one of my favorite applications of magnetic sensing. He referred to himself as the Indiana Jones of atomic magnetometry. He would wear this hat. Okay. Okay. The measuring Earth field is still an interesting thing. There are companies which are based on this, and I have one student that is working on how to use spin squeezed states in order to improve the sensitivity in those devices. And she is from the UNAM, so another nice thing to be able to mention here. Okay. I want to say a bit more about magnetic sensing. I'm going to be talking about squids now and a limit which comes from squids. So this is a paper from 1977, DC squid noise and optimization. And it's by Claudia Tesch and John Clark. Does the name John Clark sound familiar? Yeah, okay. So this, say something a bit about those two first. What is a squid? So a squid is a loop of superconductor that is interrupted by two insulating junctions that are sufficiently thin that the Cooper pairs can tunnel from one side to another. So those are called Josephson junctions, and studies of Josephson junctions is what Clark got the Nobel Prize for. And the physics of this is pretty complicated, but as an instrument, it's super simple to use. So you have a wave function for the whole superconducting, for all of the electrons in the superconductor. And that has to obey a couple of things. It has to be single valued as you go around. Meanwhile, the flux through the Aharnav-Bohm effect must affect contributes a phase there. So if there's a non-zero flux, then it has to have a non-zero phase from somewhere else. Okay. What does the Josephson junction contribute? If this phase, the current across here due to the tunneling is a function of the phases, what do the currents do? The currents flow around, and because of induction, then they change the voltage between one side and the other, and then the voltages affect how those phases evolve. So it's very complicated, multi-connected quantum system, but its use is very simple. That if you just apply a bias here, so you choose some voltage here, then you will get a current which flows through, which depends on, I'm sorry, I said that backward. You apply a current, and the voltage depends on the flux that's passing through. And so you now get a relation between flux and voltage, and that's something which is very easy to measure. Okay. Then what Tesch and Clark did was to study this, and they saw that it had a couple of parameters in it which define it, and they said, well, choose these things optimally and see how sensitive you are, see how small the noise can be. And this is a very complicated system. The interesting thing here is that all of these are coherent effects, and as a result, the current state of the squid would depend entirely on its past. And in order to break that, they put something which is not coherent, which is a resistor here, and then that, through Ohm's law, gives you a modification to this current, and it also gives you an introduction of quantum noise because the resistor is subject to 0-point fluctuations. Okay, so that's what Tesch and Clark were able to study and derive. And they said that at zero temperature, then there is still a noise due to 0-point fluctuations, and that that noise is, so this is the power spectral density divided by twice the inductance, has to be at least h bar times pi. That was their conclusion in 1977. And then in 1980, they revised this, and they said, no, actually the pi is not there because the quantum noise is of a different sort than they thought. But in any case, they get a result like this, which says that the noise in measuring the flux is related just to the inductance of the squid and h bar, which is a fundamental constant. Okay, and what is this power spectral density? Well, an easy way to think about that would be the uncertainty squared of the flux times the time that it took you to get the measurement. Okay. Okay, and so Clark, you know, got the Nobel Prize for studies of Josephson junctions. You probably don't know Claudia Tesch, but she is super important to me. She got a PhD at the University of California at Berkeley with John Clark. This limit was part of her PhD work. Then she went to Finland in order to work on superconductors applied to magnetic brain imaging. And then she went to New Mexico to become a professor, where she now studies the brain using this technique. So let me show you what this looks like. So this is an instrument called a magnetoencephalograph. It measures the brain magnetic fields. So a person puts their head into the apparatus, then the brain, because it's an electrical organ, is producing pulses of magnetic field in the neurons, and those escape out of the head because the head is, there's nothing in the head to block magnetic fields, and then those get picked up by a bunch of superconducting sensors. And then from those signals, it's possible to see what the field produced by the head was and solve an inverse problem to get what the currents in the brain were that produced them. Okay, this is me inside one of these in Finland. So she worked at the Helsinki Technical University, which now became Aalto University. And that's where I was when this was taken. So this is a modern version. It costs about 3 million euros to buy one of these. And it gives you, it's a powerful technique because it tells you where and when things happen in your brain. Okay, and that is in some sense the competition for us because we're trying to make atomic sensors which can replace this giant expensive thing. And so here is someone wearing a bunch of magnetic sensors. Each of those sensors looks something like this. So this is a miniaturized atomic physics experiment. It has a laser, it has detectors, it has atoms in it, it has magnetic field coils, it has amplifiers, and all of that allows us to get a magnetic signal from the brain in this way. Okay, so we're not as advanced as these people. These are commercial devices and these are research devices, but this is something that we're working on. Okay, so how much time do I have? Okay, so we'd like to understand better the Teschen-Clark limit. So what they said was this, that the uncertainty on the flux measurement times time divided by the inductance has to be at least h bar. And they called that energy resolution. And then we can convert from flux, and so flux squared over inductance, that's magnetostatic energy. That's why they call this the energy resolution. And we can convert that. The inductance is related to the loop area by this. Is alpha is a number of order 1, which depends on the exact shape of these wires. So we're just going to consider that to be approximately 1. And the flux, of course, is the magnetic field times the loop area. And so we can put those into this, and we get that the energy resolution is the uncertainty on magnetic field measurement times a to the 3 Hauss power times the time that it took to make the measurement divided by 2 times mu naught. And then there is this factor here, this fudge factor here. And so that has to be at least h bar. Okay, so then we now have something in terms of the magnetic field. And if we look at a to the 3 Hauss power area here, well, that's in some sense a volume. That would be somehow the volume that is around the sensor. And if your magnetic field is coming from outside, then the magnetic field is approximately constant in that region. Okay, so this then is a form of the energy resolution limit, which can be applied to things like atomic vapor sensors, which occupy space and measure magnetic fields, and compared against the energy resolution limit for squids, which are planar devices and measure fluxes. Okay, so okay, so we are then using. In the interest of time, we'll just, oh, it's too bad. Okay. So in in 2000, we published a review where we looked at the sensitivity of real instruments compared to this limit. And so this is all the squids. Each of these numbers is one squid result. This energy resolution is H bar, is this line. If we add to that the atomic vapor sensors, then we add a few more points here. If we add to that the nitrogen vacancy centers, then we add a few more points. And if we add Bose-Einstein condensates, then we add a few more points. If we add all the other technologies that we had the patients to look at, we get a bunch more points. Okay, so this energy resolution limit, which was only proven for squids, seems to be applying to everything else. Okay, and so there was speculation that this was, in fact, a true quantum limit and that the magnetic field could not be measured better than that. Okay. So if you want to read the whole story, then Giovanna and I wrote a paper in 2020 where we described the situation. We also described possible explanations. So something like, could this come from the uncertainty principle? Could this come from quantum thermodynamics? Things like that. And we conclude that no, there is no real cause of that. And then we decided that we should try to beat this limit. Okay? And so how do we beat this limit? We first look at how the magnetometer that we had available to us, which was a Bose-Einstein condensate, we look at how that could measure magnetic fields. So we start with the atoms in an initial starting state. We tip them down to the equator. We allow them to precess. And then at some point, we read out and we see what angle they have achieved. The spin system that we're using is the ground state of the rubidium-87. We did some experiments where we used just 2 states, and we do other experiments where we use all 3 states, but they're all described by spin operators. And so this picture applies to all of them. Okay. And then, okay, this graphic really didn't carry over. I'm sorry. What's the minimum I need to say about this? Okay, so in this procedure, then it turns out that the best time to read out is when the coherence has decayed by a factor of E. That is, if there is a T2 time for the relaxation of the coherence, then we should read out at T2 or approximately T2. And then we can calculate the uncertainty. We can calculate the quantum limit on this kind of sensing, that we imagine that we have some time T2. So we're going to prepare our spins, allow them to evolve, read out, and then re-prepare and read out, re-prepare, allow to evolve and read out. And I'm going to call the total amount of time available to us T. Because of this uncertainty in the spins, then I have an angular, oh, this didn't come out at all. Okay, sorry about this. There are several mathematical expressions here which got lost entirely in the transfer to the PC. I think in the interest of time, I will just say that what you get from this model is that the uncertainty on magnetic field times the square root of the time that you have available to you is at least the gyromagnetic ratio, which relates the frequency to the magnetic field, and times the square root of the number of particles, which gives you the uncertainty, angular uncertainty here, times T2, which tells you how long you can average and accumulate phase in order to do that measurement. Okay, and then that's something which is known as equation 1 of magnetometry. And if I square that and I multiply by the volume that's occupied by my magnetometer, then I get this. The energy resolution is this, that's the definition, and it should be at least this, which is from this model of the quantum noise and how it affects the measurement. Okay. Okay, so I'm losing all of my images now. Okay. Mm. Let's see what all I have here. Okay, so the point of that discussion is that this is a different limit than the one that we get from looking at Tesh and Clark and adapting Tesh and Clark. And in particular, Tesh and Clark did not have something like the density or the coherence time in it. And so if we can make a sufficiently high density and a sufficiently long coherence time, then we could beat Tesh and Clark. And then it turns out that for things like NV centers in diamond, which are immobilized spins, then there is a decoherence due to dipole-dipole coupling, which means that your relaxation rate is proportional to your density, which is to say that that product of T2 and density is going to reach some limit. And if you do the same consideration for gases, then you find that due to collisions, you get this same saturation. And the only way to beat this that we could think of was to use something that does not have relaxation associated with its two-body collisions. And that's a Bose-Einstein condensate. Bose-Einstein condensate has coherent interactions, and that continues even at higher density. Okay, so we published this in 2022. The experiment is a simple one-chamber BEC with cross-dipole traps. And inside the cross-dipole traps, we collect about 70,000 atoms. We evaporate to about 70,000 atoms in a volume that is defined by this Thomas Fermi radius, which is 7 microns. And then our readout is done using Faraday rotation probing, which is to say we pass off resonance light through and we see its polarization rotate. Okay. The system that we're using is the ground 3 states, and we can drive them with radio frequency transitions. And so here you can see it go from the lowest state to the upper states and back in a coherent way. And when we do the readout, then we can do this process with the radio frequency to tip, allow it to evolve, and then read out, and we get a signal that looks like this as it does the last few precession cycles. And then we combine that with, so that much allows us to estimate what the sensitivity should be if it remains a coherent state. To check if it remains a coherent state, we did 2 things. One was we appealed to our friends at UNAM to do a high performance computing calculation of the Gross-Pedievsky equation to see if by mean field it departs from the single domain. And it turns out it does not significantly depart from the single domain picture. And then we also did our own calculations to see how much shearing there was. In this case, the shearing works against us, so we would like to not have it. And that's pretty easy to achieve. If you work at a reasonably low field, then the ferromagnetic interaction in the condensate holds this, this distribution together. And so then we were able to have a condensate which has a volume of about 1,000 cubic microns, which has a sensitivity, if it were a pure coherent state, of about 0.01 h-bar. And then when you include the quantum noise dynamics and the noise in the optical readout, then that goes up to about 0.07 h-bar, but that's still significantly below the, this line. And so we were able to put a point on that graph that is now beyond this h-bar limit. So, and our conclusion is that h-bar is not a limit for magnetic field sensing, and we hope to see and to develop other sensors that are capable of passing this limit and thus getting better sensitivity than all of the existing sensor types. So that's it. Thank you for your attention.
Thanks, Morgan, for this fantastic lecture. Questions?
Yes, so thinking about the atom interferometry case, if this is our Bloch sphere, then we're watching a vector change in response to gravity. It is moving along the equator. So the uncertainty which contributes to our measurement is the uncertainty in that angle. And so that corresponds to one spin component as it's precessing around. Does that make sense? So if I can squeeze that spin component, then I get something which, instead of being coherent state uncertainty, is now a squeezed state uncertainty. And I can see smaller changes in angle, and in that way it improves the sensitivity. Okay, so the reason that there's a standard quantum limit, we would like to have, if we could, we would like to have the classical condition where the polarization is in some direction and the uncertainty is zero, right? And because when we look at a single atom, because it's a two-level system, we can generate polarization, but always there will be an uncertainty in some other direction. Right? And if we put together n atoms, then the polarization increases by a factor of 10, and the variance, or by n, and the variance, in fact, increases by a factor of n, and it has that ordinary standard quantum limit scaling. What we can do with entangled states is to generate a pair of, to entangle pairs of particles or a larger number of particles so that their polarizations continue to add and their deviations from the ideal direction tend to cancel. So they never cancel completely. The uncertainty never goes to zero, but we can get it so that the atoms tend to their fluctuations tend to cancel each other out. And a way to generate this entanglement is through coherent collisions.
So you show us this superposition decisions and but I don't know what it looks actually technical school science state.
So the formalism is perfectly happy to describe that situation. Can you do it in practice? The F=1 ground state does not have any inelastic collisions because the atoms are already in their lowest state. If you do this in the F=2 state, then you do get some inelastic collisions, which would mean that two F=2 atoms collide. One of them becomes an F=1, and that liberates the energy, the hyperfine energy. And that turns out to be a large energy compared to the temperature of the condensate. And so you lose atoms that way. But it's not as bad as it sounds, because if you polarize all of your F=2 atoms in the same direction, then they cannot collide and have one of them go to F=1 because of angular momentum conservation. That their total angular momentum is 2 + 2, and there's no way to get 4 out of adding something from an F=1 atom to an F=2 atom. So if you have a fully polarized state, then it's protected. And we make use of that in some of the experiments.
More questions? We have time. Well, I have a question. Yeah. I was wondering, you still have function in this experiment that you spoke about at the end? And what sort of fields are you looking to measure, to be able to measure?
Okay. You asked a big question. It turns out to be the most sensitive magnetometer ever demonstrated, but when you take into account that it's also a very small magnetometer. And so if you could put something in there that was close to it, then it could be a useful magnetometer. And there was a group at Stanford that tried to do this. Our interest in it is to use it for fundamental physics. We would like to put something inside that will affect the spin precession. We would like to do this in a co-magnetometer arrangement. That means that the F equals 1s are being used as one magnetometer, so they're precessing in one sense, and the F equals 2 are being used as a magnetometer. They precess in the opposite sense, but they're all in the same place. So the angle of precession in one should tell you the angle of precession in the other. Okay. And then if they don't agree, it's because something affected the F equals 1s differently than the F equals 2s. Why would that happen? That would happen because in one case, the electron and nucleus are aligned, F equals 2, in the other case, they're anti-aligned. And so whatever the electrons are doing, the nuclei in one case are following them, in the other case, they're anti-following them. Does that make sense?
Yeah, so you're looking at particle physics.
So we're looking at particle physics. Yes, we're doing BEC particles.
Okay.
We're building an experiment to do BEC particle.
Yeah. Thanks. Any other question? Okay.
With the spin-back magnetometers, what are the lowest magnetic fields that you can detect? What are the limits for this?
For the BEC magnetometer or for, so the BEC magnetometer is about 70 femtotesla per root hertz. And if we take one of those commercial magnetometers for measuring the brain, then that's about 10 femtotesla per root hertz.
Okay.
And it's much, much bigger. So.
Thank you.
Thank you for the presentation. My question is in the atom interferometer, if we use thermal atoms like a MOT, the velocity distributions can be inefficient at the Raman transitions. So the constants in the interferometric signal can be not so good, but the signal to noise can be good. However, if we use a BC, the constants can be improved, but the signal to noise can be poor like than a mod, because in a BC are less atoms than a mod. The question is how to find an equilibrium to in order to have a good signal to noise and contrast in the interferometric signal.
That's a great question. The history of the experimental development here was that they first started using MOTS, and then at some point they started using BECs. The first experiments to use BECs were ones that had very long flight times. So those were either experiments that were in a drop tower. So these are tall buildings with a vacuum tube in them, and you can drop your experiment down, or experiments on rockets. We started using the BECs. The advantage of the BEC there is that it's much colder, and so if you want your atoms to be in free fall for a long time, they will not expand nearly as much, and you'll be able to see more of them at the end. Does that make sense? So I would say experimentally, it was better to use MOTS for the early terrestrial measurements. And then as they go to space measurements, then it really has to be a BEC. And the reason is because of the amount of time that you can keep the atoms. And the factors that you say, number versus temperature, those are also important. But keep in mind that the interferometry protocol works whether the atom is initially moving upward or not. That it's a momentum kick. It's a delta momentum that is imparted, and then when they get recombined, then either it ends up with that delta momentum or it doesn't. And the initial momentum doesn't play a big role in generating the signal.
Thank you.
More questions? We have a few minutes. Okay, so let's thank Morgan again.
Ready? All right, it seems we're ready. Okay, so next up is Andres Luna. He's gonna continue in telling us about optoelectronic applications in quantum materials. Yes.
Okay. Oh, okay. Yeah. Now I can hear my voice. All right. Good. Right. Too much. Okay. So this is the group at Zapata. So as I mentioned yesterday, Zapata is like a multidisciplinary center. So the group is composed by physicists, chemists. You know, I have Mario, which has been working with me from master's. PhD, and now he's a postdoc at the group. Nadia is also a postdoc. So we have chemists, physicists, engineers, and undergraduate students too. So yeah, very multidisciplinary group. Okay, so since we are talking about 2D materials, I guess that the most famous, the reference or the flagship of these 2D materials is graphene, right? So back to 2004, Novoselov managed the way to thin down a single layer of carbon atoms, correct? So he did it like doing this exfoliation, mechanical exfoliation using Scotch tape. And so they demonstrated that this single layer was stable at room temperature, but also displayed very uncommon properties such as really high mobilities, really high carrier mobilities at room temperature. Okay, for this discovery, he received, they received the Nobel Prize in 2010. So this is something that you already knew, right? Perhaps what you didn't know is that in 2018, the group of Pablo Jarillo at MIT discovered that if they put two single layers of graphene and they rotate it in a very specific angle, they found out that these moire patterns formed by twisting these to the materials form flat bands. Remember the band structure? So now we have flat bands, and flat bands means that there's no more valleys up here down here, right? So the effective mass of these carriers inside the moire patterns will be huge. Okay, so the electrons will be very happy, and they demonstrated that. They did an electrical device, and they demonstrated at a very precise angle. These materials show superconductivity. Okay, so what it is important though is that carbon by itself does not display any kind of superconductivity. Right? But if you take two single layers and then you twist it, then you end up having a quantum phase such as superconductivity. Okay, so but of course, graphene is just the tip of the iceberg. Yesterday I talked about about what are transitional metal-like coordinates. So this is a single layer of them. I talked about this direct to indirect band gap crossover when you go down to a single layer, and especially TMDs based on molybdenum and tungsten are really interesting for optoelectronics since they cover, since their band gap are in the visible range. Okay, so you can imagine developing any kind of devices with these materials because they are like ultralight, low power consumption, so you can do some optoelectronics out of it. Of course, why are they so different? Because if you take the example of two standard semiconductors, let's take gallium nitride on silicon, then you have to take into account the lattice mismatch, right? Because both of them display like a really different mismatch, lattice parameters. Sorry. So if you stack gallium nitride on top of silicon, I mean, if you grow from scratch, then what it happens is you're going to start having a lot of density, a lot of these locations and the interface, right? And these locations will produce, or the consequence will be that the performance of the devices start to decrease. With 2D materials, you don't have to you don't have to worry about that. You can, since there are not covalent bonds between one and another layer, you can stack each material as you want. It's like playing with Legos. When we were kids, not so kids, because I still play with Legos. So this is like the analogy. And of course, that brings you a lot of new opportunities, right? Because you can play with flavors, and properties of these different materials. So you can have metals, even 2D magnets, semiconductors, whatever you can imagine. So this configuration can be named as a van der Waals heterostructures, since they are just interacting by the van der Waals forces. Okay. Yeah, good. So as I mentioned before, you cannot only stack these materials, you can also rotate it, right? So that is also an extra degree of freedom. So again, you can end up having these more patterns, and also you can grow lateral heterostructures, in-plane heterostructure between them. So very unique also structures that you cannot do in traditional semiconductors. Okay. Okay, good. So again, this has been already exploited and studied by different groups. So you can make LEDs out of them. You can also engineer to do some hydrogen production through catalysis. And this is very, very particular, because you can feed cells with this. And if it turns out that some cells like to eat this Dorito kind of crystals, and when they eat them, actually they start to fluoresce. Okay, and actually it turns out that when they reproduce, when the cells reproduce, actually they transmit the fluorescence. It's very funny because there are some biologists in our group, so we discussed this paper. This is why I'm able to say a few words of it. And also in 2020, they followed the same recipe that was the graphene case. They put two layers of tungsten diselenide. They stuck together and they just twisted a little bit, and they found out that depending on the number of carriers, because this is only electrically modified, you can add or take out electrons just by changing the electric field. You can go from an insulating phase to a superconductor phase and to a metallic phase. So you have these kind of strange phases, living together in this kind of systems. So yeah, so I think it is a very exciting new field in condensed matter right now. A lot of super hot topic, these twistronics and so on. So back to what we can do at Cefata, especially in the group. So we have 3D. We have three different chemical vapor deposition systems where we can grow these 2D materials. We can perform PL at room temperature, at low temperature. Well, not at low temperature, just at liquid nitrogen. We can do also time resolved PL, so we can study also the dynamics of the recombination of the excitonic features of 2D materials. We can do some AFM and some lithography to make some devices. Okay, so basically what we do is to grow our own crystals, so we can grow like different kind of systems like molybdisulfide, tin disulfide, vanadium disulfide, molybdiselenide, and so on, right? So we determine the conditions to grow these kind of materials, and then of course we play with them, we stack each other, we grow also vertical and lateral heterostructures, and we study the recombination process of the systems. Yeah, so this is like, of course, if you have different cards or different materials, you can, imagine combining a lot of things. And mainly we are focused on developing, for the last 5 years, we focus on developing a new kind of photodetectors out of these materials. So we can cover, like from 600 nanometers all the way down to a micron. So visible and near infrared range. So what I want to present today is how can we integrate these materials into optoelectronic devices. And as I mentioned, I will explain a little bit of a new kind of 2D materials that we are able to grow in the group. Okay, so let's start with the first demonstrations. So in this work, what we did is to control the PL emission of a single layer of molybdisulfide using metallic metasurfaces. So the idea or the philosophy behind a metasurface is that, for instance, if you have a plane wave coming to an interface, you're going to create, of course, once the plane wave interacts with the interface, you create Huygens sources, right? So that will eventually recreate the wavefront and will continue to transmit, to propagate, okay? However, if you manage the way to engineer or create small features below the wavelength, sub-wavelength features, such as, you space them, and then instead of having these Huygens sources, you will start having these Huygens sources at the at this structure. So with that, you can engineer the front wave, like for instance, to play with the wave to focus the light of the incident plane wave. So you can shape the light like this. You can also, you know, like turn around. You can play with the polarization and many other features of the incident light. So we took a look of what has been done, and it turns out that Wei Chen demonstrated that it is possible to focalize, focalize the second harmonic generation of a single layer of tungsten disulfide, taking into advantage the large traceability of this material. So they were able to focalize this light at 400 nanometers up to 100 micron focus. So, good. Okay, so with that in mind, we wanted to do a little bit more different. So yesterday I told you that it is possible to create polaritons into the materials if you embed a single layer of these transitional metal like electrohenides into an optical cavity, so you can have this anti-crossing PL dispersion, but also as Professor Julian comment on his second lecture, it is also possible to create a plexiton, right? So you can also couple an exciton with a plasma. Okay. Yes. So the other thing that we wanted to, to consider was the fact that since these materials are 7 thick nanometer, their optical absorption is a little bit low. So the trick to enhance the absorption is to approach the electric field near this to the materials. So there are different ways to do that. People have put like these bow tie antennas on top of these layers. So you could imagine confining the electric field inside these bow antennas. You can actually also put like some holes, so you can confine the electric field near to the transitional metal like glycogenide, or you can also put like a mirror, right? So you have like a lot of light bounding and reflecting and interacting with the 2D semiconductor. So yeah, so we mix. So we want to mix this concept. So we have 2D materials, something, a surface or a meta surface to control some aspect of some feature of the transmitted light, and a way to enhance the emission of the transitional metal like glycogenide. So this is the cartoon of our device. So we have the substrate, then a gold mirror separated with an isolator, our 2D material, and a metallic stripes on top of them. Okay, so these, the combination between the mirror, the gold and the dielectric should act as a Fabry-Perot cavity, and of course this also will support surface plasma resonance. And since we have contacts on top of them, we can also have electrical access to control the electrical doping of the MS2 monolith. Okay, so this is how the PL spectrum looks after the growth of MS2. So yesterday we centered our discussion on the exciton A, right? So exciton A was the transition of the minima and the maxima of the conduction of the value. Okay. So we have. It turns out that there is a degeneracy of this point at the valence band due to the split orbit coupling. So we also have another transition, okay? And this is why we see another peak, and we can call them as nexton. Yesterday, I was asked if there are also different many bodies inside of this situation. Yes, they are. We have also the creation of a three-body particle, which is composed in this case, since molybdenum is intrinsically an N semiconductor, we end up having two electrons and a hole, interacting with each other. So that is what we call a charge exciton or a triton. And we use, and you will see that we can use these features to actually go on and off the resonance of the plasmonic metallic metal surfaces that we will put on top of molybdenum. Okay, so once we transfer these semiconductors on the gold separated by dielectric, you can see two different things. The first one is that we had an enhancement of the PL signal due to the multi reflection, to the Fabry-Perot cavity, and then there is a blue shift of the exciton A peak. I mean, all the spectrum shift or blue shift due to the plasmon to the surface plasmon resonance. Okay, so as I told you, we decided to put these metallic strides in order to control the polarization of the emitted light. Okay, so these metallic strides were simulated in order to couple the. Okay, so you cannot see. Okay, yeah, I guess it got lost too. So we designed these bars, these metallic bars. We run the simulations in order to get the plasmonic resonance with the PL spectrum. Okay. So and of course the anisotropic nature of this bar will help us to control and manipulate the polarization of the emitted light. Okay, so we went to the clean rooms. So what I actually showing you here, this is a picture from the cell phone of the device. So this is 1 centimeter by 1 centimeter. So we have large contacts to electrically access to the semiconductors, and the stripes are like 17 nanometers thick, and the separation is about 35 or no, 375 nanometers, so on, in order to match the simulations. Okay, so this is like a Dorito in the jail, right? So in bars. Okay, so if we compare the PL signal from this crystal that is inside of the metal surface and one which is outside, you can see that we have an enhancement of the intensity, but more important, the emission is completely polarized between the parallel and the antiparallel components of the electric field. Okay, so that was very good. So we were happy about that. But however, since we had the possibility to electrically dope the semiconductor, we start wondering if we can get out of resonance and in resonance by doing electrically. So what I'm showing you here is the PL spectra at 0 bias. But then if we start putting electrons inside the molybdenum, we will generate, or we will increase the population of trions, right? So trions will act as a non-radiative pathways. So therefore, the photoluminescence emission will be off the resonance of the metasurface. or the plasmonic absorption, if you want to say. However, if we take out electrons or we inject holes inside these semiconductors, so we put it in resonance of the absorption of the plasmonic metal surfaces. So this is something that we managed to publish back in 2019, but this is a very good example of what we can do in a photonic or nanophotonic device out of transitional metal-like components. Okay, any questions about that? Because then I'm going to talk about a little bit more of material studies. Okay, good. Okay, so I would like to show today is what we think is a new kind of layer materials. At least I think these are also 2D materials, which are no longer TMBs. Okay, and the motivation is the following. So this is a roadmap from IMEC. I don't know if you guys are familiar or know what is IMEC. So IMEC is a semiconductor company that has a very aggressive policies. I mean, they are going towards other kind of semiconductors other than silicon. Okay, and I just learned that a few days. I just learned that they just invest that they're going to invest €500 million in Spain, in Malaga, I think. So they will open a research and develop company over there, and of course they will need some quantum scientists, quantum engineers. Just to okay, so what I'm showing you here is the actual technology of the transistors inside of our electronics, and these transistors are made, or the architecture is made out of FinFET. So FinFET is like the fin of the dolphins, and FET stands out for the field effect transistor. So nowadays we have these devices in our microprocessors, for instance. But it turns out that if we want to make these FinFETs even thinner and thinner, the problem is that we start having like dangling bonds and so on and quantum effects. But that traduces into a leakage current even when no voltage is applied to the gate. Okay. So that is a major problem because we are always in this quest of integrating more and more devices in a small area, right? So what they proposed is to change completely this kind of architecture. They don't want to go planar, but they want to go like vertical. You know, this is like the Mexico City, right? So when it gets like packed in the planar houses, they just start like building these skyscrapers, right? Okay, so they wanna go vertical, and they visualize that in 2030 something, it will be possible to integrate 2D materials inside of our devices. Because if you want to go planar, a very good strategy is to make the semiconductors as the sheets, right? Okay, and this is, this new architecture is called a gate-all-around or nanosheet transistor. This is the way they call it, and they say that it will offer, better and enhanced performance if we want to make the channels of this transistor shorter and shorter. Okay, so in this sense, yes. So this is how. This is a cross-sectional TM image of how a gate-all-around transistor will look like using a single layer of MOS2. So this is 20 nanometers. So you can see that, you know, it's very, very thin transistor. Okay, so at the very beginning of my career as a researcher, I thought that 2D materials will be just a curiosity, a science curiosity, right? I really doubt about, you know, an actual industrial application. But it turns out that I think I was wrong. A year ago, and this is from April, I think so. So these are like two recent papers published in Nature. They demonstrated that they are able to stack different transistors out of 2D materials. And actually, this paper demonstrated that they are able to reproduce a 32-bit microprocessor. So for those who are not familiar of what is a 32-bit microprocessor, you can think about it like this is the kind of microprocessor that you were using when you play with the PlayStation, right? So now you can play video games using a microprocessor made of 2D materials. So now things are getting serious, at least from my point of view. Okay, so yeah, video games, good. Yeah, so what's the catch? So the catch here is that turns out that you cannot directly grow these 2D materials, or they are not compatible to the temperatures of CMOS process. You know, the process that you use to fabricate microprocessors. So they need to be grown on a different substrate, okay? And then they are peeled off and stacked by one. Okay, so this is time consuming. This is almost a craft, if you will, in order to fabricate these devices. Yes, so this is just what I mentioned. So normally the direct growth of 2D materials will require higher temperatures, so such as 1,000 degrees. Okay, so you have to go down at least 400 degrees to be compatible to the back of the end of the line process in the semiconductor industry. So based on this, I mean, you know, back to TMDs are almost impossible to be or to grow at low temperature. So what I did, I challenged my students and postdoc to come with a solution to that. No, this is what you do when no, you always challenge guys. And if they respond, good. And if they don't respond, you can, you know, just take them out from the lab. No, and it took like a year, so they can, you know, bring a solution to me, and it was fantastic. It turns out that they start looking to ternary materials. So why ternary? Ternary because now you will have an extra degree of freedom to create a new material, right? And so you have you can increase the combination of materials, and they will have different stoichiometry between them. Okay, so that was the challenge, the idea, but of course the challenge was the growth. So it took a little bit for them, but they managed to do this. Okay, so what I'm showing you here is small crystals, you know, like 50 to 5 micron length. But it turns out that these crystals, you know, this is like a beautiful, you know, you have triangles, you have hexagons, and you have trapezoids over there, and so on, truncated triangles. But the beauty of this is that they managed to combine indium chlorine and sulfide or indium chlorine and selenide. Okay, and the most impressive thing, at least to me, is that they managed to grow down to 300 degrees. So 300 degrees, and we are working at atmospheric pressure. Okay, so we are now now we are in business, guys. We are really in business because these temperatures are fully compatible with the CMOS process. Okay, so again, so this is just an AFM picture of these beautiful crystals. So what we did, so what we did is to to send them to our collaborators to do high resolution TM. Doesn't matter, you don't want to do TM because it's very, very boring, but you can have like very beautiful images. So the important things here is remember the reciprocal space. So this is a pattern of the reciprocal space of this trapezoid of indium chlorine and sulfide. And the most important message is that you see these bright spots. Okay, so these bright spots means that the crystal quality, the crystallinity of this system is very high. Okay, and for some material that is grown at 300 degrees, it's very, very impressive. And the other thing is that these are the chemical maps of indium chlorine and sulfide, and it turns out that we have indium, sulfur, and chlorine, and we have them in a very special relation or stoichiometry. So we have indium 1, chlorine 1, sulfur 1, and that also doesn't happen really often. And this is the TM image, like high resolution. So we are like imaging atom by atom these materials. Okay. Okay. So of course, the first thing that I wanted to know is to know, to determine how the PL looks like, right? So I love working with excitos. Okay, so this is the Raman spectra for indium chlorine and selenide. This is indium chlorine and sulfide. It doesn't matter, it has a lot of peaks, but what I want the message here is that they are different systems. Okay, different atoms, different kind of vibrations, different spectra. Okay, and this is the photoluminescence of both of them. So so this is the PL of indium chlorine and sulfide and selenide, so they are very different, right? And just let's keep in mind this PL spectrum. The other thing that we did is to look at the dynamics of them, and of course they show also different time relaxation or relaxation times. So of course we are having a different kind of recombination phenomena taking place in both systems. Okay, but just remember this spectrum, because what we did is to pull down the sample. Okay, so we have two different features, one at low energy and high energy. Okay, so when we pull down the sample, it happened this. So this is the evolution of the PL as a function of the temperature. So we start observing that this broad and larger peak at low temperature, at low energy, will start disappear as a function of temperature. And the other thing is that the peak at higher temperature becomes very narrow. Okay. How much narrower? About 20, 25 milli-electron volts. So I just know, like for standard lasers like this is almost comparable with the full width of maximum of this laser in this point. Okay, and still, this is a semiconductor that has been grown at 300 degrees. Okay, as I mentioned, I love to play with Legos with my kids and buy my own. We managed to stack these ternary materials on top of each other. So you can see this is the Raman signature will give you the proof of it, because this is the spectrum of indium chlorine and sulfide, indium chlorine and selenide, and this is the combination of both, right? Okay. So this is ternary heterostructures, but to me, what it was also very interesting is that now we can also play with what we knew before, transitional metal-like coherence, right? So now we can take MOS2 and indium chlorine and sulfide and combine them in a ternary and TMD heterostructure. And I haven't seen these platforms before, I mean, these structures before. So we are like in a very exciting time to study all the, all the properties of this material. You know, we can not only do that, we can combine it with other systems, you know, just as tungsten disulfide or molybdiselenide and indium chloride diselenide. This is very, very strange to us for the moment. I mean, these are like the results from last month. So very exciting opportunities here. Okay. Yes. So just to summary, I mean, I just showed you before that we can grow ternary compounds using a very simple approach based on atmospheric pressure CVD. They can be grown at a temperature that are fully compatible with the back of the end of line process. So we managed to characterize them using Raman, PL, and the emission of indium chlorine and selenide is very weird, right? I also show you that it is possible to create some interesting structures based on ternary and TMDs. So this is the summary. So these are the conclusions, but you know, what is the work that has to be done? Because the thing is that there is no theoretical background at the moment, okay? So in order to explain all the data that I showed you, we need theory, right? So if you guys know some BFT good people or tight binding or you know, someone that could help us to understand what are we observing, why are they behaving like that, is like super useful. Because yes, it is like we need to do that. What else? Yeah, so this has been already done, so we can put a check. And of course, I mean, the whole purpose of this is to show you that, okay, so we have this, the growth part of the semiconductors, but of course, the big question is, what can we do with them, right? What can we study with this pattern, with this kind of structure? So there is that, from my opinion, there's still a lot of things that we can dig in, and a lot of opportunities of collaboration and so on. So with that, I think that I went very quick, but I want to thank the collaborators. So Patrice Genevet in France, you know, all the photonic part of the first thing that I present comes from his group. Mario, Shandu, my collaborators in BITS Pilani, and Mauricio at Penn State, that has a lot of TM and a lot of resources to do very nice characterization. So with that, I want to thank you for your attention.
All right. Thanks, Andres, for this very nice overview. So does anyone have a question? Yeah.
So I got a little lost at the first part of the presentation, so I don't know if you mentioned that. In the part where you have the spectrum, like the energy versus wavelength, I remember that the peak was at 650, something like that.
Right.
So my question is, what's the purpose of the device? Because I think that the peak at 600 something, it's still visible lights like red, maybe near to infrared. I don't remember actually.
Right.
So it's more like that. But is it useful that the peak is at that part and
Right. So the spectrum is really large, right? So we have different excitonic features. So the purpose is that, I mean, you cannot get rid of them, okay? But maybe you can play with them, okay? So you can decrease or increase, for instance, the broad of the peak, okay? And the main idea was, you know, to put it into resonance with the absorption of the metallic stripes. Okay, so because this is the absorption, so you can imagine that if you do narrow the peak, you can enter in resonance. So the PL will be higher. If you get out, I mean, if you make it larger, you get off resonance. Okay? So the intensity will decrease. So that was the main idea behind the integration of metallic stripes on top of these polydisulfide silicon.
Thank you.
Anyone else? I'm coming. Who? Did anyone raise their hand? Okay.
Do you have any assumptions on the behavior of the photon and phonon bands of the system you just synthesized?
Right, no. So the answer is no. I have seen some papers with similar elements, similar compounds, but it's really different. It's really different. So I mean, I have no clue about what is vibrating here, right? I have no idea, to be completely honest. Which is exciting, right? Because if that gives you a lot of you know, time to think, time to interact with other persons. Like how can we do simulate and so on. So for the moment, the answer is no. But that doesn't mean that we are looking on it.
Thank you.
Andres, thank you very much. I enjoyed a lot your talk about these ternary compounds, which are really interesting. Is there any idea of what's the crystalline structure? Are these van der Waals materials? Yeah. That's my first question.
Yeah, good. Yes, I mean, we have to index this stuff, right? So each plane needs to be indexed. We are working on it. For the moment, I mean, you can see this is an hexagonal structure. This is a mostly 3R kind of spatial distribution. But are they layered? Yes, they are. We can also exfoliate using Scotch tape. We have managed to thin down to I think 5 nanometers. So yes, so these are really good questions. We are working towards them, and yeah. So you can see this is after growth. So yeah, mostly are very thick, like 1 micron thick. Some of them are like 20, 50 nanometers. So yeah, there's still a lot of answers, questions to be answered.
And how do you exfoliate them? You put Scotch tape on top of your substrate and then kapum.
Like very basic stuff. So you put your Scotch, you start exfoliating, and then once you have the crystals on one face of the Scotch, you start like peeling off the Scotch, and then put it back into another substrate. So yeah.
How air sensitive are they?
Zero.
Really?
Zero. That is just mind blowing, because I was afraid of that. I was afraid of having oxidation and so on. And it turns out that we just measure a sample that was leave it alone during 6 months, and they still writing very, very high the exit.
My last question for now. So are there any reports of single crystal, or is this just the first report of these kind of compounds?
Yes, so there is one report, it's like that date back to the 60s, and it was powder. They use some chemical routes. I could not say you a lot of, I could not say more than that. Yes, so there are not a lot of reports.
We need to talk further.
Yes.
Okay.
Definitely.
Okay, any more questions? Yes.
Thank you a lot for your talk. I have a quick question. That the reason you're using these compounds or these specific compounds is because we can make some transistors or some electronic components to make circuits, or?
Yes. So, yeah, I mean, it started just, by a challenging question during a group meeting. But I think, I mean, to me, I think we can, I don't know if these guys can transport electricity or not. That haven't been tested. What it is important is that we can control the composition. I mean, you can put, now we can play with the elements, right? So we can play with sulfur and change to selenium. So the other now, of course, once you make the first challenge for the students, you make the second, the third, the fourth, the fifth, right? So now I ask them if they can change the metal, right? So you can change indium by aluminum, or chlorine with chromium, right? That would also, be a possibility to play around, control the growth, and try to figure out if they can be used as a transistors, right? Because that would be like the excuse to grab a lot of money from the company.
Okay, anyone else?
Thank you for your talk. I was wondering if that heterostructure that you just construct is it still like compatible with the industrial process because you're using a TMD and the ternary?
Yes. So I don't know. Maybe that is a very good question. Yes, because the way we do it. Okay, so this is fully compatible, because both of them are grown at 300 degrees. The problem is this one, right? Because what we do first is to grow MYC2. We grow them, and then we take it back from the system, and we put it in the system of the ternary machines. So it's now at this stage, it's not fully compatible, but it's just a, a proof of concept that we can, also have this versatility to form other structures that can be maybe not useful for the industry, but good for papers and so on.
All right. Another question, and how is the experimental process like to growth a digital structure?
It's super simple. You cannot imagine. It's like even I can do that. And try to find. So what we and this is also a something important to discuss because yeah. So you see this? This is just a furnace. It's just a furnace, and these are homemade stuff. So we made it. So the students in our group learn like electricity from the everything. So we build our own systems. This is just a furnace. This is a quartz tube, and this is hydrogen and argon. And then the precursors here are like solid precursors, like solid powder. So you heat up the furnace, you evaporate or sublimate the precursors, and you hope for the best in order to find the right conditions to deposit this kind of crystal. Yeah, so
Thank you.
Okay, I have one question. So is there any consensus of how to, what are the basic guiding principles to construct materials that are going to display plexitones?
Right. Right, like here, right? Yeah, so once you have formed the excitons, since, here are the structure here is, they put metallic arrays of gold or of silver, of metal. Okay, so they can support SPRs. Okay, and so once you create an exciton close by, they will be some way coupled, right? I mean, the coupling could be weak or strong. Depends. At room temperature, just the coupling is weak, so you will have like it's more like a screening from the plasma towards the exciton. So at low temperatures, apparently they create a splitting on the flexible bands.
Okay. But do you always need a heterostructure?
No.
Okay.
You don't. No, you don't. You just have to to put both systems like close to each other, try to cool down the sample, and then yes.
But I mean, you need like a layer system, right?
Oh yes.
Something that has plasmons like, I don't know, gold or something like that, and then some sort of semiconductor that is going to provide the excitons.
Correct.
I mean, but is there any chance that in bulk, single material, do you see this kind of?
I don't know, but because in bulk, what is different from bulk is that you will increase the exciton diffusion, right? In every sense. Like here, the advantage of these systems is that excitons will have more chance, more opportunity to interact with plasmas if they are like super confined.
Right.
And then, I mean, they will diffuse, of course, but this is why they put a lot of arrays, right? So to increase.
To stop them from
It's just to stop them.
Oh, thanks. Yeah. Okay. Any more questions? Yes. Absolutely.
Maybe do you think that other techniques like atomic layer deposition could work for developing these materials?
Definitely. Thank you so much for the question. Yeah, so this is something that I discussed with Rocio and Ricardo. So, these are like systems that they are like 5,000 pesos, right? No, $5,000. Okay. So The idea is that, okay, so now we have demonstrated that we can do this, right? So if we have a little bit of, more money, maybe we can do more, right? Because the things that we managed to grow, like very small pieces. So this makes no sense to the industry, okay? It makes sense to science, okay? But if you can manage to buy this, like atomic layer deposition or vacuum CDs, where you can control a little bit more, maybe you can grow into some of these. I mean, people are like IMEC, right? IMEC are following this direction very aggressively in order to create new ideas, new opportunities for semiconductor.
Right. Anyone else? Last chance? I mean, to do it officially, of course, you can discuss afterwards. All right. If not, let's thank Andres again.
Okay, we are finishing a little bit early, but that's fine. We can go slowly to it. Just a little reminder, this afternoon, we have a long session of cold atomic gases, ultra cold. Then we have a session of the postgraduate programs of UNAM and ICFO. And then is the lab tours. So make sure you're in the list, okay? Okay, so it's time to hear about the postgraduate programs of ICFO and UNAM. And first we will hear Giovanna to tell us about the program of ICFO. El micrófono lo tiene.
Ok. Genial. Perfetto, y con eso cambio. Sí. Ah, no, lo apago sana. Ok, prueba otra vez. Ah, no. Tarda un poco, pero ok. Ok. Perfecto. Ok. Okay, I see a little bit of movement in the room. Let's give them the time to. I know that you want a break, me too. But I swear that I'll be very fast. Okay, so I'm Giovanna. I work at ICFO in the Academic Affairs Unit, coordinating the training program for students and researchers. And today, with this very, very brief talk, I'm going to say something about the Institute, its mission, a little bit of the research conducted there, and in particular, research career opportunities that can be of interest for you, or at least hope so. ICFO is located, first of all, ICFO is located in Castelldefels, next to the beautiful city of Barcelona, in the northeast of Spain. And the name ICFO stands for Instituto de Ciencias Fotónicas, which in Catalan, the official language spoken by people in the region, means obviously the Institute of Photonic Sciences. And the institute was established in 2022 by a collaborative effort between the Generalitat de Catalunya and the UPC, the Technical University of Catalonia, with the aim to conduct both applied and fundamental research in the field of photonics. And in fact, research conducted at ICFO spans across all the areas of science and technology where light play a pivotal role, either as a fundamental concept or as a powerful tool for science and innovation. And as everyone knows in this room, photonics underpins a lot of technology that have become essential to our daily lives, including telecommunication, agriculture, aerospace security, and environmental sustainability, and beyond. And in fact, there are 25 research groups at ICFO, each one conducting research in a different area of photonics. And these areas can be grouped in 6 main categories: energy and environment, quantum science and technology, advanced and quantum materials, bio-nano and medical photonics, light and matter, and ultra-fast science. If you would like to dive deeper into the research conducted in this group, you could scan this QR code, which is also available in the coffee room, and you can find information about the latest publication, all the ongoing research projects, and also the contact of team members, which I strongly suggest you to contact in case you want to get more information. During this school, you have had the chance to learn about research conducted by Professor Morgan Mitchell, who is mainly involved in quantum science and tech, and or Professor Derek Chang, working in light matter and quantum science and tech, and also Sarah, when she just explained you what she's working on. So what I want to say is that often this area overlaps in terms of applications, and also the profiles of the scientists working in this group is very different, and includes engineers, physicists, also chemists, and also medical doctors. So just for you to have an idea of the scale of ICFO, since its foundation, 2,000 people have been working at ICFO, including students, researchers, and also administrative staff. So we proudly call ourselves ICFonians, and we are already a family of 2,000 people, representing more than 70 nationalities. So making ICFO a really truly international place, which I think it's one of the strongest point of ICFO. And nowadays, around 500 people are working at ICFO. We every year we welcome around 35 PhD students, and perhaps the same number of postdocs, and many more students. And also, perhaps an interesting data is that since its foundation, so far 13 spin-offs have been created at ICFO. In fact, we have a really strong knowledge and technology transfer unit made of professionals, business professionals, who help our scientists to translate their scientific result into products that can reach the market. One of the most important ICFO missions, besides its core mission of doing research, is training the next generation of scientists. And ICFO try to fulfill this mission, offering a variety of training programs, including internships, and I'm going to spend in a minute a few words about this program. And also the Institute collaborates with master programs in collaboration with other institutes and university in Catalonia. And we coordinated ICFO our own PhD program in photonics in collaboration with the UPC, the Technical University of Catalonia. And actually training the next generation of scientists happens also thanks to programs like this one, the Frontier Research School. So if you have enjoyed the school, I suggest you to take a look at the website. Generally, we organize 2 or 3 of this school per year, and on different topics, obviously related to photonics. And one is always at ICFO, and then we organize other ones in collaboration with partner institutions. So if you have a look at the website, you can check the next scheduling events. So regarding the internship, which I think can be of interest for if you are an undergraduate or master students, currently we have 4 programs available. The Maria Itzuel Fellowship Awards and the Student Research Fellowships are very similar. I'm going to explain the characteristics of them in a minute. The only difference is that this one is open to everyone, and Maria Itzuel Fellowship Awards is specific for women in science. So yeah, it's for women, but as I said, they are very similar to each other, are aimed to undergrad and master students who wants to do an internship at ICFO in up to 12 months under the supervision of one of our group leaders. There's also a stipend associated to such fellowships, and for students who are coming outside from Europe, it's correspond to 900 euros per month. And there's one eligibility criteria, apart the fact of being obviously an excellent and motivated student, which is being enrolled in an academic program during the entire internship. If you are interested in these 2 programs, actually the calls are open and the deadline is 6 November. If you are interested in these programs, but not right now, be aware that we have 3 calls per year, so you can check the next one, which will open in March. Anyway, here is the QR code where you can scan, and you will find exactly the page where you will find the application. If you have any questions, I'm going to be here today and tomorrow. Together with me, there's the academic affairs, Veronica. You have well, she gave a talk yesterday, so please reach out to us and ask any question you have or any doubts. We'll be very happy to help you. Then I would like to say a few words regarding this program, the SPIE ICFO Research Fellowship Program, because this program is connected to this school, the Frontier Research Schools. It aims at students who participated in the school, and for this school we have 2 fellowships available. In case you are interested, you should show your interest through this form. If you scan this QR code, you will be able to go to this form. And the characteristic of the program is very similar to the one that I have explained. As you can see, the material that you have used to apply for the school will be used for the selection of the students, and also feedback coming from the group leaders who participated in the school and the organizer. So if you are interested, please show your interest through this form. And then the last program available is the summer fellowship. This program is a little bit different, but if you are interested in a shorter period, if you want to spend a shorter period, then it can be a good option. In this case, students spend about 3-4 months in one of ICFO research groups, and generally the program is, the time frame is quite strict. It's during the summer break, which I'm not sure if corresponds to your summer break, from June, July to September, October. And this program is really nice. There's also a training program associated to it. Students can participate to lab tours. They can participate to summer lectures, transferable skill training, and also social activities. If you are interested in this program, call will open in January. Again, if you want more information or have any doubts, reach out to us. I want to mention that that this initiative exists. This is the Catalonia Quantum Academy. It's a platform led by ICFO that brings together many partners you can see research institute entities and also private company with the aim of strengthen the training in quantum science. Why I'm mentioning this? Because career opportunities are available also through this platform. As you can see here, there's a call for research fellowships. It's closing soon, but other opportunities will be available again. If you are not interested, if you are not an undergraduate or master student, but you are a PhD or postdoc, you can also check opportunities available for you on the web page. As I said, ICFO collaborates with different master programs. I'm not going through this program because I don't have time, but I want that you know these programs exist. So if you are interested in studying abroad in Barcelona, these are the programs available, with which ICFO collaborates: the Master in Photonics, Master of Multidisciplinary Research in Experimental Sciences. I can give you more information if you want. Master in Quantum Science and Technologies. So take a look and let me know if you need any information. And then as ICFO, then if you are interested in a PhD, then ICFO also coordinates its own PhD in photonics. Since its foundation, more than 300 students graduated from this program. As you can see, 70% of them are in Europe right now, and 46% in Spain. And I put this data just for you to check what they are doing now. 63% of them are still in academia after the PhD, and 31% in industry. And the other one, they are pursuing perhaps a career like mine, working now in academic affairs. And this is just a slide that I put to show you that we have alumni from Mexico. You have had the chance to meet Roland and Silvana, also Cesar, who is not in this slide, but then you see Arturo Villegas is now a technical project manager at Lux Quanta, the company that was in the presentation 2 days ago, and Montserrat Alvarez. It's a way to show you that people are doing very different things after the PhD in different places in the world. Calls for PhD are open right now, so you can scan the code and check. But I would like to show these slides just for you to know that we have 4 calls per year available. So the ones right now open is the fall call, and then in winter there will be another one. In spring and summer, two other ones, but you can see they are a little bit different because we have institutional fellowships on offer during the winter and the summer call. And then there's what we call admission period in fall and spring, which means that funds should be available through group leaders. And so in case you want to start a PhD, you should apply through the website, but then the group leader should have fellowships available for students. I forgot actually that I put these slides. This is in case you want to have a look at any career opportunities available in photonics. This is also an initiative led by ICFO called Carla Camps. They organize annually, many events per year. Sometimes they are also online, so you can participate even if you are here, in which they are exploring all the career options available in the field. So take a look at the website if you want. The last slide. I just want to leave you our contacts. As I said, you can find here my email. Also, If you want to follow me in LinkedIn, I always publish polls open events of interest for you. And here you have the contact of the head of academic affairs, Veronica. We are here again. We are open to any questions. And if you have doubts, we can talk during the coffee breaks. I would love to get in touch with you.
And now I will ask Alberto Güijosa, the coordinator of the PCF, the program of UNAM, to tell us the information.
Good. Yes, okay, so hello, you've heard now, thanks to Giovanna, you heard of a set of very nice alternatives, very interesting alternatives to do your graduate work. So I'm happy now to be here to tell you some other alternatives. So as Daniel said, I'm going to talk about the local alternatives here at UNAM. Clearly, by your being here, you're showing definitively that you love physics. And just knowing that, let me tell you that we'll be very happy to welcome you to the physics graduate program at UNAM. So in Spanish, it's Postgrado en Ciencias Físicas, and the acronym for that is PCF. So you'll see that somewhere scattered along the slides. Now, our graduate program, we're proud to say, has a very distinguished tradition and always with high academic standards. So its origin dates back to 1939. Its modern incarnation dates from 1997. And its most recent updating in terms of our curriculum dates from 2019. We offer 3 graduate degrees, 2 master's programs. The one of most interest to you in this school is the Master in Physics. We also have a Master in Medical Physics, and we have a doctoral program in Physics. Our graduate program is held together by a strong collaboration between 10 departments in total scattered throughout UNAM. So these are 7 research institutes in total, plus 2 schools, plus a research center. And they're actually, in fact, around 4 different cities in Mexico, most of them here in Mexico City. So 7 out of the 10 are here in Mexico City. We have a total of around close to 400 graduate advisors at your disposal in different topics. At any given time, if you count only enrolled students, we have somewhere around 240. So basically 80 in the Masters in Physics and around 140 in the PhD program. And as you might imagine, we're involved both at the master's level and the doctoral level. We're involved in all possible types of modes of work and topics of work. So we do theoretical, experimental, and computational physics in a huge array of topics. We work both in local groups, but also in all sorts of international collaborations. This very school is, of course, a show of the fact that we have international collaboration with our friends at ICFO. Let me just show you briefly a very small sampling of various examples of collaborations. So starting with large international collaborations, we participated DESI, ALICE, HAWK. Now switching to just a few examples of research labs at UNAM, starting with some that are of close interest for you at this school. There's micro and nanophotonics lab at the Institute of Nuclear Sciences. There's cold atoms and quantum optics lab at the Institute of Physics. There's an applied optics lab at the Institute of Nuclear Sciences. There's an optical tweezers lab at the Institute of Physics, and so on and so forth. Just to give you examples from other areas, there's a space instrumentation laboratory at the Institute of Nuclear Sciences. There's a refinement of crystalline structures lab, and so on, further and further away from your interest. And of course, there are also many diverse examples of work in both theoretical and computational research. So the list would be too long to show, but just naming here a few. In particular, certainly many topics related to your topic of choice, having to do with quantum information. Now, both at the master's level and at the doctoral level, we're divided into 7 sort of sub-communities, 7 fields of research, as we say. The 2 that are of greatest interest for you, given your attendance at this school, are the field of quantum, atomic, and molecular physics, which has in itself 3 subfields, and also the field of optics and photonics. So each of these sub-communities has a group of advisors at your disposal and a group of talented students who would be with you along the road. The curriculum at the master's level prioritizes fast access to research. So in the interest of time, I won't stop to mention out each of the steps. But basically, what you need to know is that this is a very flexible and adaptable curriculum. Essentially, your first year is mostly devoted to courses, and your second year is mostly devoted to your research. This is at the master's level. One of the most important things that you need to know is that how to get in. So at the master's level, we have 2 admission processes per year, so 1 each semester. So the next call for admissions will be announced just next month, November 2025. And then you'll find out the details in our website in particular. But then just so that you get a sense of it, the online application happens in February, at least for this call, it will happen in February. So that's when we register as an applicant. And then there's an application process, and then the semester, this will be for the semester that begins in August of 2026. So that this is your next opportunity if you're interested. And if not, every 6 months after that, the same process repeats. So the basic requirements for admission to our master's program is naturally an undergraduate degree in physics or some related area with proximity to the field of interest, a grade average at or above 8 on a scale of 0 to 10. Knowledge of Spanish for the master's level, knowledge of Spanish is crucial, knowledge of English, and of course to pass the entrance exam. The entrance exam has 2 stages. One is a written part, and then there's an oral part. And it deals with the natural topics that one covers at any undergraduate institution when you study physics. 5 subjects, which are classical mechanics, electromagnetism, quantum mechanics, thermodynamics, and modern physics. We offer free preparatory courses, and they're offered online, so you can access them from any part in the world, or in particular in this country. And those are offered naturally to aid in preparation for the exam. And I should also note that it is possible, under certain requirements that you can read in the instructions, to request exemption from the written stage of the entrance exam, if you meet those conditions. I'll also say a few words about, let me see how I'm doing on time, about the admission to the doctoral level, to the PhD program. So again, there we have 2 admission processes per year, so one per semester, and the timing is exactly the same. So the next call for admission will be in November, the registration as an applicant online will be in February, and the semester will begin in August of 2026. And again, the information is on our website, of course. There's a specific type of entrance exam for admission to the doctoral program. Its acronym is CASI, and it evaluates 2 relevant aptitudes for entrance at the doctoral level, which are, on the one hand, you have to defend a specific research plan that would take you to your first doctoral research paper, research publication. And then coupled with that, we evaluate your knowledge of 2 introductory courses in your field of specialty. We have structured these exams such that it's in your benefit in the sense that it facilitates early start towards research. So you get to know your advisor in advance, and more importantly, you know precisely which specific project you will work on, and you can even start working on that before you enter. But an important feature of this process then is that it requires from you substantial interaction with your prospective advisor months in advance of the process. So that's something to keep in mind. Now you can read all of the details about this entrance exam, this CASI exam. We have some guidelines for applicants, one set of guidelines for applicants and separately for advisors in our website, of course. I should also point out the costs if you're coming from abroad in particular. The basic message is that the costs are actually not very significant for the admission process. And very importantly, there are no tuition costs at UNAM. There's an admission fee, there's an entrance exam fee, and there are certain documents that you need to get apostilled and whatnot. So there are some payments you need to make along the way just for the application process, but those are minor. And the beauty of living in a public university is that tuition is completely free. So your quality education is free. Now, coupled with that, now that you know that you don't need to worry about tuition, you do need to worry about your living expenses, of course. You do need to live somewhere and eat something. So for that, our main source of funding are CECITI fellowships. So CECITI is the acronym for the Ministry of Science in Mexico, or the Secretary of Science. And we're fortunate that for many years, for many decades, they have offered fellowships to cover graduate studies in Mexico, be they from Mexican students or from foreign students. That doesn't make a difference. And those are meant for you to pay for your living expenses. So the point is that because our graduate program is a part of the national system of graduate programs, this funding is available to you, would be available to you as students of ours. Or more specifically, or more precisely, what you're allowed to do is to apply for this fellowship. And but of course, the number of available fellowships is subject to the Ministry of Science's budget. The fellowships themselves are actually quite reasonable in terms of what they cover as far as your living expenses. So at the master's level, it's this amount in Mexican pesos per month throughout the full 2 years of the master's, and at the doctoral level, it's this amount per month during the 4 years. So if you don't know how to translate Mexican pesos to your currency, just know that this is a very reasonable amount. Now, importantly, the admission to our graduate program by itself does not guarantee a fellowship. That's important for you to know. And also, the name of the game will be for you to strive to have the best possible results in our admission process, because that would increase the likelihood of the fellowship. So it's not just a binary decision of being accepted or not, but performing as best as you can, so you can be better situated in this prioritized list for fellowships. The application, the way the process is set up is that CECITI mandates that the application is submitted only after enrollment. And in particular, for those of you coming from abroad, that would mean that you need to be here in Mexico before the application. And so semester starts, then you apply. But importantly, even though I do emphasize that the admission does not guarantee a fellowship, I should tell you that thus far, all of our students' applications have been successful. So good to have that finance. The new call for applications is published at the beginning of each year, around February or March. So you can look at the 2025 version at this particular link if you want. And then once you're here, other than having your living expenses solved, there are also different types of funding for traveling to conferences and schools, for equipment, research stays, and so on, coming from either UNAM itself or of course research grants of your advisor. So you are then, as I said, all of you cordially invited to either of our master's programs or our doctoral program at the physics graduate program at UNAM. We come back to this point that you're here because you love physics, clearly. So never lose sight of that along all your travels, along all your travails in these years. So our best advice, of course, for all of you is to keep studying with passion, and to make sure you enjoy these precious years as much as you can, because they go by very fast. So I leave you here with 3 final slides. This is the QR code where you can download our digital brochure for the Masters in Physics program. It's in the coffee room as well. Okay, so that's one item. Similarly, for the doctoral program, this is the QR code. And finally, these are our contact possibilities. So certainly our website. This is our main email address for administrative queries, and for academic queries, you can talk to the professors in charge of the respective research fields. Well, these are other points of contact. So again, thank you for your attention, and we'll leave it there.
Thanks, Alberto. Now, Pablo is going to tell us the details about tours for the labs.
All right, thank you. Everyone who signed up for a lab tour, I hope you check the lists that are in the coffee room that will tell you which tour you are on and which group you are within that tour. Okay, so Francisco is gonna be for tour 1. Angel, you're gonna follow him for tour number 2. They are going to be outside. They're gonna wait for everyone to meet them, and then you're gonna go to their respective tours, okay? If you have any questions, please go to them or me.
If you want a shot of coffee before going to the tour, you can have it. It's ready, the coffee.
Also, please, this is very important, especially if you're going to Instituto de Ciencias Nucleares, have your badge with you. Okay? Thank you.